Hello, everybody. I am not in class, as y'all can see, but I will be presenting problem 48, and I will first read it to y'all, and hopefully it makes sense. But if it doesn't, don't worry, because I will be breaking it down and proving it. So, again, this is problem 48, and it reads, if M is a finite subset of a segment S and P is a point of S, there is a segment T that is a subset of S and contains P, but contains no point of M that is not P. So although this sounds a bit confusing, if we break it down, all we have right now is a segment S, we'll call it AB, and we also have M, which is a finite subset of S, and we'll call it x1, x2, x3, xn. And if we draw it out, we'll get something like this. And yes, I purposely color coordinated to where S is black and M is purple, and it'll be the same throughout the whole proof. So hopefully that will help. You're welcome. So now that we have defined M and S, we now have to build a segment T where it's a subset of S and contains P, but contains no point of M that is not P. So originally when I read this, I thought that we had to create 3 segments and then somehow combine them with another segment. I don't know, I was so confused. But that's not the case. We have our M and we have our S. So now we just have to build a segment T where it just contains M, only one point of M. And there are 6 generic cases that needs to be proven for any xn. So now we will be looking at all 6 cases, but what I'm going to do so you could follow along better, I'm going to start from the far left side of segment S. As you can see on the very top picture, I have the start and the green arrow going towards the right. And our first case is where P is between A and X1. We just create segment T with endpoints A and X1. We are now looking at case 2, and that's when P equals X1, and our segment T will have endpoints A and X2 because it only contains X1, which is P. So now it gets a little tricky here. This is case 3, and that's when P is between X sub I and X sub I plus 1. And we'll say that I is an element of 1, 2, 3, n minus 1. And for this case, we'll have T equal, or our segment T will be X sub I and X sub I plus 1. So we are now looking at case 4, and case 4 is basically when our P is either greater than or equal to X sub 2 or less than or equal to X sub n minus 1. So basically this just means that J is between 2 and n minus 1. So yeah, we have P equals X sub J, and J is an element of 2, 3, 4, n minus 1. And for this case, our segment T will just be X sub J minus 1 and X sub J plus 1. So if you see at the top picture, you could tell all the cases we've covered. We are finally where P equals X sub n. This is case 5, and for this, we'll just have our segment T have endpoints X sub n minus 1 and B. We finally made it to our last case, case 6. This is whenever P is between X sub n and B. Our segment T will have endpoints X sub n and B, And yep, that is all. So really quick, I just wanted to show again all the cases we covered. All the pink dots are P, and we started from the left and ended at the right. And this is just a picture to show where we have created all our segment T's. It's hard to tell because they're all together, but with this, we have proven that if M is a finite subset of a segment S and P is a point of S, there is a segment T that is a subset of S and contains P, but contains no point of M that is not P. Okay, that is all of my proof. I will be watching the video or the recording of this class later today. So I guess I'll try to answer the questions y'all have. Of course, any comments, nice ones, mean ones, are welcome. I won't be there, so I guess that's good. Yeah, that is all. Bye!